Hello, welcome to my video series of algorithms. This is part 11 of Module 1, Sorting Algorithms. In this video, we will continue our discussion of the Radix sort algorithm. Recall that in the previous video, we discussed the general idea of Radix sort. It is a non-comparison based sorting algorithm and extends the bucket sort algorithm with more practical applications such as sorting large numbers and strings. We also introduced two Radix sort styles. We have the least significant digit first Radix sort, or LSDF Radix sort. And we have the most significant digit first Radix sort, or MSDF Radix sort. We presented the LSDF Radix sort in the previous video, and today we will discuss the MSDF Radix sort. Recall the LSDF Radix sort, where we perform bucket sort based on each position of the elements, starting from the last position all the way through the first position. In other words, the sorting phases are performed in the backward order. On the other hand, for MSDF Radix sort, the sorting phases are performed in forward order. Now, the question is, are these two algorithms identical in terms of time and space efficiency, and do they cater to different applications? It turns out that reversing the sorting order will bring much more differences between these two algorithms than we think. Let's consider the first question. Why do we need MSDF Radix sort given the existence of LSDF Radix sort? To answer the question, consider sorting the following set of strings. The strings contain single letters that are different, except one string that also contains a different letter, but it's very long. To sort the strings with LSDF Radix sort, we will pad the strings to the same length as the longest string, and then sort the padded strings backward. You can see that all sorting phases that compare the special character $sign with the letter Z will not make any change to the order of the strings. And all those comparisons are wasted. What makes things worse is that these nonsense comparisons dominate the entire execution of the algorithm. In short, it wastes a lot of computation and space. Now, if we step back and think about how much computation we need to solve the problem, we immediately realize that a single sorting phase is sufficient. That is, we sort the strings with their starting positions. This is why we need MSDF Radix sort. So, from the above example, it is easy to conclude the advantage of MSDF Radix sort. It can terminate as soon as no ambiguity regarding the sorting order presents. Hence, the best scenario time complexity for MSDF Radix sort is O(m plus k), W times faster than the LSDF Radix sort. We can also derive that when the lengths of the strings are highly uneven, we may consider using MSDF Radix sort. However, note that although MSDF Radix sort has these advantages, it also has a worse time complexity comparing to LSDF Radix sort, which will be made clear later in this video. Let's begin our discussion with details of the MSDF Radix sort algorithm. If we simply reverse the order of the sorting phases, will we obtain the correct results? We will try reversing the order with the example we had in the previous video. We begin with performing bucket sort on the first position, and here is the result. Things still look right. Then we move on to the next phase. Now you can see the problem. The string THE, which should be ranked the last, has been ranked to the second. Recall that to define lexicographical ordering, we should indeed consider the most significant positions first. However, if we do not record the resulting rankings and let the subsequent sorting phases disrupt the rankings, we will not be getting the correct results. So, a simple fix is that we shall respect the rankings generated by the former sorting phases. In other words, Subsequent sorting phases should be independently applied to small string groups that share the same prefix, but not among strings that have different prefixes. We will illustrate the idea with the same set of strings. We first sort them based on the first position. We see that this sorting phase partitions the strings into two subgroups, the strings sharing the prefix G and those sharing the prefix T. We know that the second group contains only one string, therefore, no further sorting is needed. In the second sorting phase, we will only sort strings in the first group. The sorting further divides the strings into two subgroups, the strings sharing the prefix GE and those sharing the prefix GO. The first group contains only one string, and no further sorting is required. Here is a snapshot after the third sorting phase. We can see that it further divides strings sharing the prefix GO into strings sharing the prefix GOL and strings sharing the prefix GOO. At last, with the fourth sorting phase, all resulting string groups contain only one string. At this point, we can terminate the sorting. Recall that compared to the LSDF Radix sort algorithm, the MSDF Radix sort algorithm terminates after 4 sorting phases. We will write the pseudocode of MSDF Radix sort using recursion. We will define a recursive function, MSDF Radix sort recursive, by adding 3 parameters, s, e, and p, to the original function interface. The recursive MSDF Radix sort performs bucket sort on the s to the eth strings based on the characters in their pth positions. Here is the pseudocode for the recursive function. In line 2, we handle the boundary case where only one string needs to be sorted or where the radix has gone out of range. In lines 3 to 5, we define the key information for sorting as the pth position of the strings within the range. In line 6, we perform the bucket sort. In lines 8 to 10, we recursively sort strings that share the same p-long prefixes. Note that we increase p by 1 when going deeper with the recursion, which corresponds to the MSDF Radix sort direction. And we can have this driver function, which initiates the recursive function call with the entire set of strings and the first position as the key information. Finally, let's analyze the MSDF Radix sort algorithm. Its correctness is obvious, as it directly implements the definition of lexicographical ordering. For time complexity, first recall that the bucket sort algorithm takes O(n plus k) time. Because MSDF Radix sort is applied to string groups, let the average size of each string group be lowercase n, and the number of groups be p. In this case, we have small n times p be the uppercase n, or the total number of strings to be sorted. To sort each group, it requires O small n plus k time. To sort p groups, the time complexity becomes O p times n plus k, or O capital N plus p times k. Because p, the number of groups, is upper bounded by the number of elements n, the above time complexity, O capital N plus pk, is in O n times k. In other words, it will take O n times k time to sort each position. Given that the algorithm contains W phases, the time complexity of the MSDF Radix sort algorithm is O W times n times k. For space complexity, we first assume that the algorithm is executed sequentially and not in parallel. In this case, we will be performing at most one bucket sort at a time, which requires O n plus k space. We also need to span OWN space to store the input strings. The overall space complexity is thus OWN plus k. Finally, I would like to discuss more about the use cases of MSDF Radix sort. While Radix sort is a non-comparison based sorting algorithm, we can always sort strings using comparison-based sorting. To do that, we simply compare two strings character by character to determine their relative orders. This process will take OW time, where W is the length of the two strings. Then, we can couple the process with the existing comparison-based sorting algorithms, such as quicksort, and obtain algorithms that run in OWN log n time. Now, compare the time complexity of all string sorting algorithms that we have learned so far. We can see that the best time complexity is achieved with the LSDF Radix sort. It explains why we don't simply modify the existing comparison-based sorting algorithms for string sorting. We also see that the worst time complexity corresponds to MSDF Radix sort, which is even worse than comparison-based sorting. So, should we always choose comparison-based sorting over MSDF Radix sort? To answer this question, first recall that the advantage of MSDF Radix sort is that it can quickly split the strings into smaller groups by sorting the most significant positions of the strings. Strings within each smaller group share a common prefix. Since each group is expected to only contain a small number of strings, it becomes faster to sort strings within each group using comparison-based sorting. Now, say we have used MSDF Radix sort to sort the first n positions of a set of strings. The total time we have spent on this step is O, M, N, K. If we assume uniform distribution of characters in the entire alphabet, we will now have k to the power of m small groups, and each group contains n over k to the power of m strings on average. To sort each small group using comparison-based sorting, we will need O W minus m times n over k to the power of m times log n over k to the power of m time. Since we have k to the power of m groups in total, the time needed to sort groups becomes O W minus m times n times log n over k to the power of m. Simplifying the term, we get O Wn log n minus Wn log k to the power of m plus mn log n over k to the power of m. Taken together, we have spent OM and K time on sorting the first n positions of the strings using MSDF Radix sort. And we spent O Wn log n minus Wn log k to the power of m plus mn log n over k to the power of m time to sort the remaining positions using comparison-based sorting. Now, decompose the time spent on the second phase into two parts, as shown here in the red and purple, respectively. You will find that the red part corresponds to the time required by direct comparison-based sorting without MSDF Radix sort. The purple part corresponds to the efficiency gain after MSDF Radix sort. Now, compare the cost of MSDF Radix sort with the gain. We realize that when n is larger than k to the power of m, and w log k is larger than k, we have the gain overweigh the cost. In other words, when the strings being sorted are long, there exists an optimal value m, such that sorting the first n positions of the strings using MSDF Radix sort will likely lead to some performance gain. In summary, we have discussed the MSDF Radix sort algorithm in this video. The MSDF Radix sort algorithm could terminate earlier than the LSDF Radix sort and run in OM plus K time in the best case scenario. However, it has a worse time complexity of OWN times M plus K compared to LSDF Radix sort. When implementing the MSDF Radix sort, we should avoid implementing it with recursion to save space. We should also combine MSDF Radix sort with comparison-based sorting for better time efficiency. Thank you for watching and see you next time.